There is a silence in the outer dark, a deep and profound cold that has lasted for billions of years. In that silence, things sleep. They are not dead, only waiting, preserved in a frozen perfection at the edge of our perception. But now, something in that silence has stirred. Something has awakened. From the unimaginable distances of our solar system's final frontier, a shape is moving. It is not fast, not flashy. It does not streak across the sky like a warning shot. Its motion is glacial, majestic, and utterly inevitable. It has been falling toward the heart of our solar system for millions of years, a silent pilgrim on a journey that began before humanity ever walked the Earth, and we have only just become aware of its approach. Its name is Bernardinelli-Bernstein, a comet so colossally, unnervingly massive that it redefines the very word. At 137 kilometers across, its nucleus alone is a worldlet of ancient ice and rock, a frozen leviathan that makes every other interstellar visitor we've ever seen, including the fleeting 3-eye ATLAS, look like a mere pebble. It is 10,000 times more massive than that tiny, fast-moving stranger. Scientists call it a time capsule, a pristine relic from the dawn of our solar system, carrying within its frozen heart the untold secrets of our cosmic birth. But its sheer scale, its timing, and the bizarre nature of its arrival prompt other, more uncomfortable questions. Why is it coming now? After 4 billion years of silent, frozen slumber in the deep dark, what alarm clock rang? What force, what event, nudged this sleeping giant from its eternal rest and set it on a collision course with the inner solar system? And the most pressing question of all, are we prepared for what it might reveal? Stay with me, because by the time we are done, you will understand that this is not just another comet. This object, this phenomenon, changes everything. It challenges our models, our understanding of the solar system's history, and perhaps even our place in the cosmos. If you are as captivated by these cosmic enigmas as I am, if you feel that pull to look up and wonder what else is moving out there in the void, then go ahead and like this video and subscribe to the channel. Stay with us as we track BB's inexorable journey inward. We are living through a once-in-a-species event, and you will not want to miss a moment of it. Leave a comment, tell me where you are watching from, what the hour is in your corner of the world. I want to feel the global scale of this audience, all of us looking up together. And tell me, what is your first thought when you hear about this comet? Do you feel awe, or a prickle of something else? This object isn't just big, it is, in a very real sense, wrong. To understand why, you must first put yourself in the shoes of an astronomer. Imagine a lifetime spent studying comets. You know them as small, fragile things, icy rubble piles a few kilometers wide that swing past the sun, light up with a temporary atmosphere for a few glorious weeks, and then vanish back into the void, their substance depleted. You have catalogued their orbits, measured their compositions. You understand their behavior. They are part of a known, predictable family. And then, one day, you find something that shatters that comfortable understanding. In 2014, buried in the immense archival data of the Dark Energy Survey, astronomers Pedro Bernardinelli and Gary Bernstein spotted a faint, moving pixel. At first, it was just one anonymous dot among countless others. Space is full of rocks. But as they tracked it, measured its slow progression, and analysed its light, a disquieting realisation began to dawn. This was not normal. This was an outlier of the highest order. Designated C 2014 UN 271, it was soon christened Bernardinelli-Bernstein, or BB for short. The initial distance estimates were staggering. This thing was already active far beyond the orbit of Neptune, in a region where the Sun is a mere pinprick of light, and water ice should be permanently frozen solid. When the Hubble Space Telescope finally managed to fix its gaze upon it, the measurements that came back were humbling. The nucleus, the solid core of the comet, was not 10 or 20 kilometers wide. Preliminary analysis suggested a diameter of 85 miles, 137 kilometers. To put that in a perspective that is almost impossible to grasp, the famous Comet Hale-Bopp, which captivated the world in 1997, was about 40 kilometers across. BB is more than 3 times larger. It is not a comet in the traditional sense. It is a dwarf planet that has, for some unknowable reason, decided to pretend it is a comet. It is roughly 10,000 times more massive than the typical comets we see, and its very existence in the reservoir we call the Oort Cloud forces us to reconsider what we thought we knew about that distant realm. Remember 3I ATLAS? That was the tiny, fast-moving interstellar object that zipped through our system, a visitor from another star. It was small, fragile, and moving at breakneck speed. BB is the antithesis of that. It is colossal, slow, and stable. It is a native, but a native from the farthest, most forgotten frontier. And now, it is coming home. Here is the first layer of the mystery, the thing that makes BB truly bizarre. Comets are not supposed to be this big. Our leading models of solar system formation suggest that most comets are small, accreted from the clumping of ice and dust in the outer protoplanetary disk. They are essentially rubble piles, loose collections of material held together by their own weak gravity. But BB is different. Its sheer size and its apparent spherical shape suggest it formed differently. It may be a protoplanet, a building block of a larger world that never quite made it. It is not a loose pile of rubble. It is a solid, structured body. And that single fact raises profoundly uncomfortable questions. Why does something this massive exist in the Oort Cloud? How did it get there? Was it formed in place, which challenges our models? Or was it violently ejected from the inner solar system during the chaotic planetary migration billions of years ago? And why, after an eternity of frozen silence, is it suddenly active? Because here is the crucial, early clue that signaled BB was anomalous. It began brightening years ago, when it was still way out beyond Neptune, at a distance where the sun's warmth is barely a whisper. At those distances, around 20 to 25 astronomical units, water ice cannot sublimate. It simply isn't warm enough. Water ice needs heat. But BB was glowing anyway, developing a faint coma. Something else was venting from its surface, something far more volatile than water, something that can turn from solid to gas at the bitter temperatures of the deep outer system. In 2024, the Atacama Large Millimeter Submillimeter Array, ALMA, trained its incredibly sensitive radio eyes on BB. What it found was remarkable. Powerful, organized jets of carbon monoxide, CO, were erupting from specific fixed regions on the comet's surface. This was happening at around 16.6 astronomical units from the Sun. For reference, Saturn orbits at roughly 9.5 AU. BB was still twice as far out as Saturn, and it was already actively venting a hypervolatile gas. Carbon monoxide sublimates at incredibly low temperatures, much lower than water. The fact that BB has enough CO to produce visible, powerful jets at this distance means it possesses massive internal reservoirs of this primordial gas, preserved in a deep freeze for billions of years. Most comets lose their hypervolatiles like CO early in their lives. By the time they venture into the inner solar system, they are mostly just water ice. But not BB. BB is a time capsule, sealed and locked away until now. Mainstream astronomers are thrilled by this. They call it a pristine sample from the solar system's birth, a relic from the era when worlds were still coalescing from the nebula. Study BB, they say, and you are studying the raw materials that built Jupiter, Saturn, Uranus, and Neptune. They are almost certainly right. But there is another question lurking beneath the surface, a question that makes some scientists shift uneasily in their chairs. Why now? If BB has been sitting in the serene, deep freeze of the Oort Cloud for 4 billion years, utterly undisturbed, why did it suddenly, in the cosmological blink of an eye, start its long fall inward? What changed? Was it a purely random event, a simple roll of the cosmic dice? Or was there a trigger? Some theorists point to galactic tides. Others whisper about a passing star, a ghost from our past. A few consider something else entirely, something unseen, a hidden hand that reached out and nudged this giant awake, sending it tumbling toward us. We will explore those possibilities soon, but for now, sit with this reality. An object the size of a small moon, filled with ancient gases we have never seen in such abundance, is moving on a trajectory that defies easy explanation. It is heading toward the sun, and we have no definitive idea what truly set it in motion. That is not just interesting, it is terrifying. Because if we do not understand what woke BB up, how can we possibly predict what else might be coming? How many more giants are lurking in the Oort Cloud, waiting for the same mysterious push? And what happens if the next one isn't heading for a safe perihelion beyond Saturn? What if the next one is heading straight for us? Hold that thought, because the mystery of BB's awakening is about to get much, much stranger. Imagine a bowling ball sitting on the edge of a vast, silent ice rink. It has been there for 1,000,000 years, motionless, perfectly balanced in its own private equilibrium. Then, without any visible cause, without a tremor or a sound, it begins to roll. Slowly at first, the movement is almost imperceptible, a shift measured in millimeters per century. But it is moving. The central question, the one that claws at the mind, is not that it moves, but why? What unseen force, what subtle imbalance, what ghostly hand finally gave it that initial, fateful push? This is the exquisite puzzle of Bernardinelli-Bernstein. For over 4 billion years it sat in the Oort Cloud, that unimaginably vast and diffuse spherical shell of icy debris that forms the true outer boundary of our solar system. The Oort Cloud is not a place. It is a concept of distance so grand it defies human intuition. It begins roughly where the influence of the planets fades, around 2,000 astronomical units from the Sun, and extends outward, potentially as far as 100,000 AU, or even more. At that staggering distance, the Sun is not a dominant star. It is merely the brightest among many in a black sky, a faint beacon whose gravity is a whisper. Objects there drift on orbits that take millions of years to complete, their motions sluggish, their existence solitary. They are not supposed to leave. They are supposed to stay in that deep freeze, forever circling the frozen fringe, unless something powerful, disturbs them. So what disturbed BB? The search for an answer leads us down paths of cosmic detective work, each hypothesis more thrilling and unsettling than the last. The first and most accepted theory involves galactic tides. We must remember that our solar system is not an isolated island. We are part of a great spinning carousel of stars, gas, and dark matter, the Milky Way galaxy. As we orbit the galactic center every 230 million years, we move through a complex gravitational landscape. The combined pull of billions of stars, the massive central bulge, and the enigmatic halo of dark matter creates tidal forces, much like the moon's pull on Earth's oceans, but operating on a scale so vast it is difficult to comprehend. These tides are not constant. They ebb and flow, they pulse and oscillate as we pass through regions of varying density. The spiral arms, galactic disk. Some dynamicists, scientists who specialize in the motion of celestial bodies, have proposed a specific model, a 14,400-year tide pulse scenario. The idea is that roughly every 14,400 years, a particularly strong and resonant galactic tide sweeps through the outermost reaches of the Oort Cloud. Objects like BB, perched at the very edge of the Sun's gravitational influence, feel this tidal pull most strongly. It is a gentle but persistent tug, a cosmic nudge that over vast stretches of time slowly alters their orbits. The changes are incremental, almost negligible in a human lifetime, but over millennia, these tiny perturbations accumulate. A stable, circular orbit becomes slightly elliptical. The ellipse becomes more pronounced, stretched like a rubber band, until one day, the orbit is no longer stable. The object breaks free from its gravitational moorings and begins the long, slow fall toward the inner solar system. This model is elegant and fits within our understanding of galactic mechanics, but it is still speculative, a compelling narrative woven from the threads of mathematics and observation. Flooring there is the passing star hypothesis, a theory that feels like it belongs in an epic poem. Our sun, for all its brilliance, is not alone in its journey through the galaxy. Stars move, they dance, they occasionally pass near one another. Millions of years ago, long before humans walked the Earth, another star, a silent, nuclear-fired wanderer, might have drifted through the outer reaches of our Oort Cloud. The European Space Agency's Gaia mission has been meticulously mapping the positions and motions of over 1 billion stars in our galaxy, creating an unprecedented cosmic movie that allows us to rewind time. Some researchers, analysing this treasure trove of data, have suggested that a star did pass near our solar system in the distant past, close enough for its gravity to act as a gravitational rake, stirring up the frozen debris at the solar system's edge. A passing star does not need to come particularly close to have a profound effect. Even at a distance of several thousand astronomical units, its gravitational field can exert a significant tug on Oort Cloud objects. These tugs are small, individual kicks, but over the millennia, they add up. An object's orbital energy changes by a minuscule amount. Its path shifts by a fraction of a degree. Over millions of years, these tiny changes compound, eccentricities grow, and eventually, an object like BB finds itself on a new trajectory, one that points directly toward the heart of the solar system. If this is what happened to BB, then its awakening was not random. It was an inevitable, if delayed, consequence of an ancient stellar encounter, a cosmic billiard shot played out over eons. But here is where the comfortable explanations begin to fray at the edges, where the scientific curiosity transforms into a low-grade unease. If either of these scenarios is true, if galactic tides or passing stars are routinely responsible for shaking comets loose from the Oort Cloud, then we should expect more objects like BB. Many, many more. The Oort Cloud is not sparsely populated. It is estimated to contain trillions of icy bodies. If these large-scale gravitational forces are constantly perturbing them, then BB is not an anomaly. It is a harbinger. It is the first of a coming wave, the leading edge of a storm of comets that has been set in motion by the galaxy's slow, inexorable churn. This raises a question that nobody in the astronomical community wants to ask out loud, but everyone is thinking. How many more are coming? Not all astronomers accept these dramatic models. A more conservative school of thought argues for random diffusion. In this view, the Oort Cloud is a dynamically hot environment. The orbits of objects within it naturally evolve and decay over time due to their own mutual, weak gravitational influences and the constant background whisper of the galaxy's tide. No external trigger is needed, just patience. Billions of years of patience. Eventually, through a process of random walk in orbital energy space, some objects will inevitably lose enough energy to fall inward. It is cosmic roulette, and BB's number simply came up. That is all. But there is a problem with this clean, statistical explanation. It feels too neat, too convenient. Because BB is not just any comet. It is monstrously massive. It is unusually structured, as we will see. And its timing, arriving in our current observational era, in the age of Hubble, James Webb and ALMA, at the precise moment when we possess the technology to study it in unprecedented detail, feels almost orchestrated. It feels, to a part of the human brain wired to seek patterns, like something wanted us to see it. That is where the whispers start, the quiet speculation in conference hallways, the uncomfortable theories discussed over late-night drinks. If not galactic tides, if not a passing star, if not random chance, then what? Could there be something else out there? A hidden planet of significant mass? A dense, localized clump of dark matter? Something we haven't detected yet? Something that has been quietly, gravitationally perturbing the Oort Cloud for eons, and whose influence we are only now beginning to sense? There is a story, perhaps apocryphal, but told and retold because it captures the mood. A respected researcher, after a few drinks, once confided to colleagues, "I don't believe in hidden planets. I really don't. The data is too flimsy. But something huge must have disturbed that object. The math doesn't work otherwise. The odds of something this big falling in now, by pure chance, are astronomically low." And when the math doesn't work, you are left with two stark possibilities. Either your fundamental assumptions about the solar system are wrong, or there is something out there you are not seeing. So which is it? Are our models of the Oort Cloud stability and population fundamentally flawed? Or is there a massive unseen perturber lurking in the dark? And if so, why can't we find it? Is it simply too faint, too far, too small to detect with our current telescopes? Or is it something stranger, something our instruments and our paradigms are not designed to recognize? We will explore those haunting possibilities soon. But first, we need to understand the path BB is taking, because its trajectory is not just a line in space. It is a storybook, and the story it tells is filled with big, unsettling clues. Those clues suggest that whatever woke BB up didn't just give it a gentle nudge. It fundamentally altered the very geometry of its path through the cosmos. And that geometry is deeply, profoundly weird. In the silent clockwork mechanics of the solar system, orbits are more than just paths. They are narratives. They are frozen histories, recording an object's origin, its past encounters, its violent adolescence, and its quiet maturity. If you know how to read their language, the subtle language of inclination, eccentricity, and perihelion, you can reconstruct a biography billions of years old. Most members of our solar system family move in a state of harmonious, flat order. The planets, the asteroids of the main belt, and the majority of comets all orbit the Sun in a relatively flat disk known as the ecliptic plane. This is not a coincidence, it is a birthright. The solar system itself formed from a spinning, flattened disk of gas and dust. Every planet, every asteroid, every speck inherited that initial spin, that primordial momentum. They all circle the Sun in the same general direction, like cars on a cosmic racetrack, their orbits tilted only slightly relative to one another. It is a stable, predictable, and beautifully orderly arrangement. And then there is Bernardinelli-Bernstein. BB is the stranger who doesn't just walk against the traffic, it drops in from the ceiling. Its orbit is tilted at a staggering 95.5 degrees relative to the ecliptic. That is not just inclined, that is nearly perpendicular. Imagine the flat plane of the solar system as a giant round table. The planets are marbles rolling along grooves on the table's surface. BB is not on the table. It is a marble dropped from the ceiling above, falling straight down through the plane of the table, cutting a path that is almost exactly vertical. This is bizarre. This is not how comets from the Oort Cloud are supposed to behave. While the Oort Cloud is spherical and objects within it can have any inclination, highly inclined orbits are still a minority. A near-perpendicular orbit is a glaring anomaly. Why does this matter so profoundly? Because orbital inclination is a powerful diagnostic tool, a fingerprint of an object's dynamical history. A low-inclination orbit, one that lies close to the ecliptic, generally suggests a quiet life. It hints that the object formed in the protoplanetary disk and has remained there, undisturbed by major gravitational encounters, its path a testament to a peaceful existence. A high-inclination orbit, on the other hand, is a scar. It is the indelible mark of violence, of a gravitational interaction so powerful it kicked the object out of the plane. A close encounter with a giant planet, a near miss with another large body. These events can impart a tremendous gravitational torque, literally lifting an object into a steeply inclined orbit. And a near-perpendicular orbit? That suggests something beyond mere violence. It suggests deep, ancient chaos. It speaks of a time when the solar system was a wild, untamed place, a cosmic shooting gallery where objects were flung about like pebbles. One explanation lies in what dynamicists call the deep Oort chaos model. The Oort Cloud, for all its vastness, is not a calm, serene reservoir. It is dynamically hot. The objects within it do not move in stately parallel circles. They have been jostled, stirred, and perturbed for billions of years by the combined gravitational influences of passing stars, the persistent pull of galactic tides, and the distant memory of planetary migrations in the solar system's youth. Over eons, this constant gravitational noise has randomized many of their orbits. The Oort Cloud is a chaotic mess, a celestial ballroom where everyone is dancing to a different tune, moving in all directions and at all inclinations. So perhaps BB's perpendicular orbit isn't unusual at all. Perhaps it is simply a product of that grand billion-year chaos, a statistical inevitability in a cloud of trillions of bodies. One of them was bound to be on such a path. Undermined there is another idea, a more radical and controversial one, that sends a thrill down the spine of every astronomer who considers it. What if BB is not originally from our solar system at all? What if it is a captured interstellar object? Billions of years ago, during the early, crowded days of the solar system's life in its birth cluster, stars were packed much closer together. Planetary systems were still congealing from the nebula, and it was a time of great gravitational instability. Objects could be easily ejected from one fledgling system and, by a stroke of fortune, captured by the gravity well of a neighbouring star. If BB is such a captured interloper, that would elegantly explain its weird orbit. Its extreme inclination would not reflect a violent history within our system, but rather the orbital plane of its original alien solar system. It came from somewhere else, a frozen refugee from another star, and was captured by the sun's gravity, trapped in the outer Oort Cloud. And now, after billions of years in frozen exile, something has disturbed its slumber, and it is finally falling inward, a messenger from a stellar sibling we have long since lost. Paycheck this theory is, for now, highly speculative. There is no direct smoking gun evidence, but it fits. Compare BB again to 3I_Atlas. Atlas was unequivocally interstellar. It came screaming into the solar system on a hyperbolic trajectory, swung past the sun and left, never to return. It was a tourist. BB is different. BB is on a massive but very much bound elliptical orbit. It will swing inward, reach its closest point to the sun, and then head back out to the depths of the Oort Cloud. It is not leaving. It belongs here, or at the very least, it has been here long enough to be considered a naturalized citizen. Its orbital mechanics are unforgiving, and they tell a story of belonging, however strange its path may be. Ping this steep inclination is not just a curious factoid. It has profound consequences for BB's journey. It affects everything. It determines how BB will interact with the giant planets as it crosses their orbital planes. It changes how solar radiation heats its asymmetrical surface. It influences the behaviour of its outgassing jets. As it moves inward, it will slice vertically through the orbital planes of Saturn, Jupiter, and even the inner planets. Each crossing is a potential gravitational encounter, a chance for a giant planet to give it a slight gravitational tug, altering its path in ways that are subtle but crucial over long timescales. There is a powerful concept in celestial mechanics known as orbital resonance. This occurs when two objects have orbital periods that are a simple ratio of each other, like 2:1 or 3:2. When this happens, their gravitational interactions can become synchronized, amplifying their effects over time. The dance between Jupiter and Saturn is shaped by near resonances, and their gravitational influence sculpts the entire architecture of the outer solar system. Could BB, on its strange perpendicular path, briefly enter a resonance with one of the giant planets? Could that resonance change its path, make it more unstable, more unpredictable, more dangerous in the long run? It is possible. Unlikely, given the briefness of its passage, but possible. And that sliver of uncertainty bothers astronomers deeply, because we crave predictability. We like to know where things are, where they are going, and what they will do. BB's orbit, with its steep alien inclination and the unpredictable planetary perturbations it might encounter, introduces an element of chaos into our clean models. And chaos is hard to model, hard to predict, and impossible to prepare for with absolute confidence. Some theorists find the inclination unsettling for a reason that borders on the philosophical. They argue, quietly, that it feels engineered, not naturally evolved. The specificity of it, the near-perfect perpendicularity, feels too precise, too unlikely to be a simple product of random gravitational scattering. This is fringe thinking, to be sure. Most mainstream scientists dismiss it outright as pattern-seeking nonsense, but the feeling persists in the background, a nagging whisper. The orbit is just too specific, too unusual. Could a phantom planet, a massive unseen body, have deliberately pumped BB into this trajectory over millions of years? Could an unseen hand have sculpted its path? We will explore that ghost soon, but for now consider this. An object's orbit is its fingerprint, and BB's fingerprint tells a strange, uncomfortable story. A story of forces we do not fully understand, operating in a past we can only simulate. A story of something, somewhere, exerting an influence we cannot quite see. And if we cannot fully understand the path BB has taken, how can we hope to understand what lies inside it? How can we predict what it will do as it feels the sun's growing warmth? Because what we see on the surface, those jets of carbon monoxide, those bursts of light, are merely symptoms. The real mystery, the profound secret, lies locked within. It lies inside that massive nucleus, inside the very structure of the object itself. And recent observations are finally giving us our first, tantalizing glimpses of what Bernardinelli-Bernstein really is. And what we are seeing is not what anyone expected. Cottons are notoriously secretive. They are cosmic coquettes, putting on a brilliant show with their glowing comas and spectacular tails, yet revealing very little of their true inner nature. You can watch them from Earth with telescopes. You can send sophisticated spacecraft like Rosetta to orbit them and land probes on their surface. But truly understanding their internal structure, the arrangement of their ices, the presence of voids, the strength of their materials, is one of the most challenging problems in planetary science. You cannot simply crack one open. You cannot drill into its heart from 1 billion miles away. You have to infer. You have to deduce from limited, indirect data, the way it spins, the way it outgasses, the way it reflects light. In the case of Bernardinelli-Bernstein, that data is both a treasure trove and a profound puzzle, pointing to an object that defies simple classification. The Hubble Space Telescope has been watching BB for years now. Hubble, even in its later years, remains a peerless instrument for precise imaging. And what Hubble saw when it finally resolved BB's nucleus surprised everyone. The nucleus was not jagged or irregular. It was not the lumpy, potato-shaped rubble pile that characterizes comets like 67P Churyumov-Gerasimenko, which Rosetta studied. Instead, BB's nucleus appeared nearly spherical, smooth, uniform. This simple observation is seismic in its implications. It suggests that powerful internal forces have shaped this object over billions of years. Small bodies, held together by nothing more than their own meagre gravity, are irregular. Their shapes are dictated by random accretion and impacts. But when an object becomes large enough, its own self-gravity becomes a dominant force. It pulls itself inward, overcoming the material strength of the rock and ice, moulding itself into the most efficient shape for a gravitational field, a sphere. This state is known as hydrostatic equilibrium, and it is one of the key defining criteria that separates planets and dwarf planets from smaller asteroids and comets. BB appears to be in or very close to this state. That suggests significant internal pressure and self-gravity. It suggests that BB is not a loose collection of rubble, but a consolidated, structured world. Spherical objects in space typically fall into two categories. The first is planets and large moons, where immense gravity crushes the material into a sphere. The second is differentiated bodies. Differentiation is a fundamental planetary process. In the early hot solar system, as large bodies formed, the heat from radioactive decay and impacts would melt their interiors. In this molten state, gravity would cause the heavier elements like iron and nickel to sink to the center, forming a dense core, while lighter materials like silicates and various ices would rise to the surface, forming a mantle and a crust. BB is too small to be a full-fledged planet, but its size and shape strongly suggest it might be differentiated. It might have layers, an outer crust of dark, refractory organic material and silicates, a mantle of water ice mixed with complex organics, and deeper still, layers of more volatile ices like carbon dioxide, and perhaps even a core of rock and metal. This would make it far more akin to a miniature planet, a protoplanet frozen in time, than to a typical comet. ALMA, the revolutionary radio telescope array in the high deserts of Chile, added another critical piece to the puzzle in 2024. When ALMA mapped the carbon monoxide jets erupting from BB's surface, it found they were not random, chaotic bursts. They were organized. They emerged from specific, fixed regions on the nucleus and persisted over time. This tells us something crucial about the interior. It is not uniform. There are pockets, reservoirs of volatile CO gas trapped beneath the surface, sealed in by an overlying layer of less volatile material. As BB moves closer to the Sun and its subsurface temperatures slowly rise, these reservoirs heat up. The pressure builds until the overlying crust fractures and the gas escapes in a focused jet. The presence of so much CO is, in itself, extraordinary. Carbon monoxide is a hypervolatile. It sublimes from solid to gas at temperatures as low as 24 Kelvin, minus 249 degrees Celsius. The fact that BB has enough CO to produce powerful, visible jets at 16 astronomic units means its interior is still loaded with this primordial stuff. Most comets lose their hypervolatiles quickly after their first few passes near the Sun. It vents away into space. But BB, having presumably never visited the inner solar system before, has been cold enough for long enough to preserve massive amounts of CO deep within its layered interior. It is a pristine vault, and the lock is just now beginning to click open. Flaming here is where the science ventures into the thrillingly speculative. Some researchers are now proposing a stratified chemistry model for BB. Imagine it not as a homogeneous ice ball, but as a cosmic onion, layers upon layers, each telling a different chapter of the solar system's history. The outermost layer is a crust of dark, complex organic molecules and silicate dust, a rind built up over billions of years. Beneath that, a thick mantle of water ice, the most abundant ice in the solar system, probably mixed with other organics. Deeper still, a layer of carbon dioxide ice, dry ice, and at the very core, or in isolated pockets, vast reserves of pure carbon monoxide ice. Each of these layers would have formed and condensed at different temperatures and pressures in the early solar nebula. Each was preserved in sequence as the young protoplanet was ejected to the deep freeze of the Oort Cloud. Now, as BB approaches the Sun, these layers are warming up sequentially, from the outside in. First, the outermost crust warms, but nothing happens. Then, as heat slowly conducts inward, the CO begins to sublimate at the deepest, coldest levels, driving the early activity we see now. Later, as it gets closer, the CO2 ice will begin to turn to gas. Finally, around perihelion, the water ice will erupt into furious activity. Each phase will produce different outgassing behaviors, different jet chemistries, and a dramatically changing brightness. There is another, even more exotic idea floating through the scientific community: the concept of phase-trapped hypervolatiles. This is the notion that at the incredibly low temperatures of the Oort Cloud, certain volatile compounds can exist in unusual, metastable crystalline structures, forms of ice that are not stable at higher temperatures. These exotic ices can act like cages, trapping molecules of gas, like CO, within their crystal lattices. The gas remains trapped, under pressure, for billions of years, until the object warms to a specific, critical temperature. At that point, the crystalline structure undergoes a phase change, collapses, and releases all the trapped gas in a sudden, dramatic burst. So perhaps BB's current activity is not just simple sublimation, but the breakdown of these ancient, weird ices, releasing their imprisoned volatiles in a process that is more like a chemical explosion than gentle evaporation. This has profound mechanical implications. Internal pressure from these trapped gases can fracture the crust from within, creating cracks and fissures that become the vents for the jets we observe. Over time, as more and more gas escapes, the internal structure could weaken, fragments could break off, the comet could change shape. Some comets, like the famous Comet Shoemaker-Levy 9, fragment dramatically when they pass too close to a giant planet. Others disintegrate when they get too close to the Sun. Will BB fragment? Its large size and strong gravity suggest stability. Large objects are much harder to tear apart. But internal pressure is a powerful force, and if BB truly has a complex layered interior, those layers might delaminate under stress, like the layers of an onion being peeled apart. Each fragment would be a unique sample, revealing a different epoch of solar system history, a core fragment rich in rock and metal, a mantle fragment of pure water ice, a crust fragment coated in complex organics. What we know for sure is that BB is not behaving like a typical small comet. Small comets have erratic, unpredictable jets that flicker on and off as they rotate. Their activity is a sign of their fragility and simple structure. But BB's jets are organized, powerful, and persistent. They speak of an internal engine, a complex, planet-like system of insulated reservoirs, pressurized chambers, and engineered like vents working in concert. This is not typical cometary behavior. This is weird. This is the kind of sustained geological activity you would expect from a cryovolcanic world like Jupiter's moon Europa or Saturn's moon Enceladus. Icy moons with internal heat sources that drive plumes of water vapor and organic molecules into space. Not from a comet. Brightness. So what is BB really? Is it a comet? Is it a dwarf planet? Is it something entirely new, a missing link between the two? And does the distinction even matter? The answer is a resounding yes. How we classify BB determines everything about how we study it. It dictates what scientific questions we prioritize, what kind of missions we propose and fund, and what potential dangers we prepare for. Because if BB is more planet-like than comet-like, then its behavior as it approaches perihelion could be radically different from anything we have ever witnessed. It could be more violent, more volatile, more spectacular, and more unpredictable. But we are getting ahead of ourselves. Before we can plan how to study this awakening giant up close, we must first understand its timeline. How long do we have? When will it make its closest approach? And what does that mean for our narrow, fleeting window to unlock its secrets? Because here is the uncomfortable, pressing truth. BB moves with a slow, majestic grace, like a skyscraper adrift in the void. But that slowness is deceptive. Time is running out. The window to study this object in its current, relatively pristine state, before it is forever changed by the sun's embrace, is narrower than you think. Punished it. A skyscraper made not of steel and glass, but of dark, dirty ice. This is not a metaphor. Bernardinelli-Bernstein is a literal geological scale structure, a mountain of primordial matter frozen solid, coated in a layer of ancient, complex organic tar, drifting through the vacuum. And it is coming. Its motion is slow, inexorable, a function of orbital mechanics that operates on a timescale far removed from human urgency. It is the celestial equivalent of a glacier carving into the sea, a slow, majestic, and unstoppable event. But herein lies the paradox. Even though BB's approach is measured in years and decades, there is a palpable mounting urgency in the astronomical community. Because every day that passes, every week, every month, BB is changing. It is a living laboratory, and the experiment is running in real time. Once it changes too much, we lose our one and only chance to study what it was, a pristine, untouched relic from the dawn of time. Slashing BB was first spotted retrospectively, a ghost in the machine, hidden in archival images from the Dark Energy Survey dating back to 2014. But it wasn't identified as the extraordinary object it is until years later. By the time astronomers realized what they were looking at, BB had already been on its inward journey for years, perhaps decades, maybe even centuries. Its orbital parameters suggest it began its long fall from the Oort Cloud long before humans invented the telescope, before we even understood the heliocentric model of the solar system. We are merely the lucky, or perhaps fated, generation that happens to be looking in the right place at the right time to notice its approach. Discharged right now, as we speak, BB is still far from the Sun, cruising through the outer solar system beyond the orbit of Neptune. Its current distance fluctuates between 16 and 18 astronomical units. To provide some context, Neptune orbits at about 30 AU, Saturn at 9.5 AU, Jupiter at 5.2. BB is still in the outer neighbourhood, but it is on the inbound track, and we know its destination with high precision. Astronomers have calculated its trajectory with incredible accuracy. It will reach perihelion, its closest approach to the Sun, in January of 2031. That perihelion will be at a distance of about 10.9 astronomical units. This is a crucial point. BB will not come close to Earth. It will not threaten the inner planets. Its path will take it just beyond the orbit of Saturn. It is a safe distance by any measure, but 10.9 AU is close enough for solar heating to fundamentally and irrevocably change everything about it. This gives us a critical observation window. The period between now and roughly 2028 or 2029 is when BB will undergo its most dramatic and scientifically valuable transformation. Right now, it is in its early stages of activity, venting carbon monoxide in subtle, organized jets. This is gentle outgassing, but as it drifts inward, crossing inside the orbit of Uranus and approaching Saturn's domain, the heat will intensify. Water ice, the most abundant volatile in its composition, will finally reach its sublimation temperature. When that happens, the coma, the fuzzy, glowing cloud of gas and dust that surrounds the nucleus, will thicken dramatically. The jets will intensify, becoming violent, dusty plumes. The comet will brighten by orders of magnitude, transforming from a faint smudge, visible only to the world's largest telescopes, into an object potentially within reach of advanced amateur equipment. And all of that glorious activity, that spectacular show, will be a problem for scientists. Because the very coma and jets that make it bright and beautiful would also obscure the nucleus. They will act like a thick atmosphere, hiding the surface, making it impossible to study the geology of the nucleus, to map its active regions, to understand the root causes of its behaviour. The most valuable observations, the ones that probe the true nature of this beast, need to happen now, in the next few years, before the curtain of gas and dust drops, before BB the primordial protoplanet becomes BB the spectacular but obfuscated comet. This has triggered a quiet scramble among scientists. Hubble is dedicating precious observing time to it. ALMA is listening intently to its molecular whispers. A global network of ground-based telescopes is tracking its every move. Large automated optical surveys are capturing petabytes of data, monitoring its brightness and colour for subtle changes. Every new observation adds another piece to the puzzle. Every spectrum reveals a new molecule in its coma. Every high-resolution image shows a subtle shift in its surface features. But it never feels like enough. There is never enough time, never enough data, never enough certainty. The feeling is that of trying to drink from a fire hose of information, knowing that the flow is temporary. Looming over all of this is another risk: fragmentation. Some comets do not survive their close encounter with the Sun. The combined thermal stress from uneven heating and the rotational forces from outgassing jets can cause them to spin up and tear themselves apart. If BB fragments, it would be both a scientific disaster and a unique opportunity. A disaster because we would lose the chance to study an intact, primordial mini-world. The pristine interior, the layered structure, the geological context, all of that would be lost, replaced by a cloud of glittering debris. But it would also be an opportunity, because fragmentation would expose fresh interior material that has never been touched by sunlight or solar wind. We could sample ices that have been locked away for 4.5 billion years, providing an uncontaminated look at the solar system's original ingredients. Will BB fragment? Its great size is its greatest strength. Its gravity is strong enough to hold it together against all but the most extreme forces. But internal pressure, as we've discussed, is a wild card. If it has a differentiated, layered interior, those layers could separate. The core could break from the mantle. The crust could shatter. It would be like watching a planet being unmade in fast forward, each fragment a chapter of a geological history book being torn out and scattered to the wind. Striped even if it holds together, its appearance will change beyond recognition. Right now, it is a faint, anonymous speck. But by 2030, as it approaches perihelion, it could become a visible, if faint, object in a medium-sized telescope. Imagine that. A comet the size of a small moon, glowing in the outer solar system, its tail perhaps visible as a faint smear, a testament to the sheer scale of the event. It would be a rare and special sight, but a temporary one. After its January 2031 perihelion, BB will begin its long swing back outward. It will fade, cool down, and its activity will cease as the ices refreeze. It will retreat back into the darkness from whence it came. Its orbital period is measured in millions of years. Once it leaves, it will not be back. Not in our lifetimes, not in the lifetime of our civilization, not in the lifetime of our species. This is a once-in-a-species opportunity, a chance to study an object that has existed unchanged since the solar system was in its infancy, and we are the generation alive to witness it. So, the urgency is real, a tangible pressure in the halls of observatories and NASA centres. Scientists are pushing for more telescope time, more funding for observational campaigns. Some are even proposing missions, crazy, ambitious, borderline impossible missions to send a probe to BB, to fly past it, to smell its gases and map its surface up close. Most of these proposals are pipe dreams, relegated to the what-if sections of conference presentations. The engineering challenges are Herculean, the funding non-existent for such a high-risk, high-cost endeavour. But the desire is there, burning brightly. Because we know with a chilling certainty what is at stake. We know what we will lose if we do not act, if we let this giant pass by without unlocking its secrets. Smuggling, and here is the most haunting part of all. We are not just watching a comet, we are watching something ancient and vast awaken from a billion-year slumber. Something that has slept in the cold and the dark since before the first complex life formed on Earth. And now, for reasons we do not fully comprehend, it is waking up. It is moving, changing, heading toward the light. And we may never fully understand why. We may never know what set it in motion, what forces, what events, what invisible hands guided this giant out of the shadows and into our field of view. But it is here now. And in a strange, poetic way, it is watching us as much as we are watching it. Its ancient light, carrying secrets from the beginning, is now falling on our telescopes, on our eyes, on our civilization. And that thought, that deeply uncomfortable existential thought, is one that should keep us all awake at night, looking up at the stars and wondering what else is stirring in the deep. In the vast, silent tapestry of the cosmos, patterns are the universe's way of whispering its secrets. In science, in nature, in the very fabric of reality, patterns are the signal amidst the noise, the telltale sign that something real, something significant is happening, something that demands an explanation. And right now, a pattern is emerging in our solar system, a subtle but persistent signal that is making dynamicists and astronomers profoundly uncomfortable. Over the last decade, have witnessed a cluster of unusual objects entering or passing through our celestial neighbourhood. The odds of this being a simple, random occurrence are disturbingly, tantalisingly low. Let's rewind the clock. October 2017. Astronomers at the Pan-STARRS survey in Hawaii spot a faint, fast-moving object. It is unlike anything they have seen before. It is given the name Oumuamua, Hawaiian for scout or messenger from the distant past. It is the first confirmed interstellar object ever detected. It is small, dark, and remarkably elongated, tumbling through space. It doesn't behave like a typical comet. There is no visible coma, no clear evidence of outgassing, yet its trajectory shows a slight, non-gravitational acceleration, as if some unseen force is gently pushing it. Scientists argue for months, for years. Is it a fractal dust aggregate? A shard of a shredded planet? A hydrogen iceberg? To this day, nobody knows for sure. But one fact is undeniable. It came from another star. It passed through our system, a silent visitor from the galactic void, and then it was gone. Greenhouse 2019. 2I Borisov arrives. Another interstellar object, but this one is different. It is unmistakably a comet. It sports a brilliant diffuse coma and a faint tail. Spectroscopy reveals familiar molecules: cyanogen, diatomic carbon, water vapor, and carbon monoxide. Borisov behaves, in almost every way, like comets from our own solar system. This is both reassuring and perplexing. It suggests that the chemistry of planet formation is universal, that the ingredients for life, or at least for complex chemistry, are common throughout the galaxy. But it also raises a pointed question. If interstellar comets are this common, why did we only start seeing them in 2017? Then came 3I ATLAS, small, fast, and interstellar, a fleeting blur that was barely studied before it vanished back into the interstellar dark. And now, we have Bernardinelli-Bernstein. Not interstellar, but massive, ancient, and anomalous in its own right. 4 profoundly unusual objects in less than a decade. Is this a statistical fluke, a simple consequence of our improved technology? Or is it a signal? Is something happening? The conservative and perfectly reasonable explanation is observational bias. Our telescopes are exponentially better than they were a generation ago. Surveys like Pan-STARRS, the Dark Energy Survey, and the upcoming Vera C. Rubin Observatory are scanning vast swathes of the sky with unprecedented depth and frequency. We are looking harder, with better eyes, and of course, we are finding more things. We are finally seeing the traffic that has always been flowing through our cosmic intersection. There is nothing mysterious about it, just the steady march of technological progress revealing a universe that was always there. But some dynamicists, the mathematicians of celestial motion, are not entirely convinced. They have run the numbers. They have calculated the expected rate of interstellar object encounters based on stellar densities in our local galactic neighbourhood, the velocity distributions of stars, and the gravitational cross-section of our solar system. And the numbers, while fuzzy, do not quite add up. We are seeing slightly more than we should. Not by an overwhelming margin, not enough to declare a revolution, but enough to be noticeable. Enough to make a scientist lean back in their chair, frown, and wonder. If the cluster is real, if it is not just an artifact of our improved vision, then something is happening. Something has changed. The most likely culprit, the source of this potential perturbation, leads us back to the Oort Cloud. The Oort Cloud is not just vast, it is the single largest structure in the solar system, a vast reservoir containing trillions of icy bodies. And it is not static. It is a dynamic, seething sea of orbits, constantly jostled by external influences. If something is perturbing the cloud more than usual, if some external force is shaking this cosmic snow globe with a newfound vigour, then we would expect a cascade of objects to be dislodged, to fall inward. We would see more comets, more anomalies, more surprises. This is the heart of the trans-Oort perturber hypothesis. The idea is that something massive, something we have not yet detected, exists in the space beyond the Oort Cloud and is gravitationally stirring the pot. This is not necessarily the hypothetical Planet 9, which is thought to orbit within the inner Oort Cloud region. This is something farther, grander. Perhaps a substellar object, a brown dwarf, a failed star, that passed through the outer reaches of our solar system millions of years ago. Its gravity, though distant, would have been like a plough through a field, scattering icy bodies before it. Or perhaps it is a dense, localized clump of dark matter, a gravitational knot in the invisible fabric of the cosmos. Or maybe it is something we haven't even conceived of yet, a class of object that exists only in the theoretical margins of astrophysics. The hypothesis is wildly speculative, but it is tantalizing because it provides a unified explanation for the cluster. It explains why BB, Oumuamua, Borisov, and Atlas are all arriving now. It suggests an external trigger, an event in the recent astronomical past that disturbed the Oort Cloud and set multiple objects on wildly different trajectories on their way inward. And if that is true, then Bernardinelli-Bernstein is not an isolated giant. It is merely the first. There are others already on their way. Other giants, other anomalies, other mysteries are lurking in the dark, slowly falling toward the inner solar system, and we haven't detected them yet. Critics, rightly, counsel restraint. Selection effects are powerful forces in science. Telescopes and the scientists who use them are inherently biased toward finding unusual objects because unusual objects are interesting. They make headlines. They secure funding. Careers are built on the discovery of anomalies. So, perhaps we are over-interpreting. Perhaps this cluster is an artifact of human curiosity, a self-fulfilling prophecy of our own making, and not a reflection of a changing cosmic reality. Perhaps there is nothing unusual happening at all. But there is a story, one that circulates in hushed tones. A researcher, a respected dynamicist, ran thousands of Monte Carlo simulations, modelling the natural evolution of the Oort Cloud under every conceivable condition. And their code consistently failed to produce the observed cluster of unusual objects within such a short time frame. The statistics were just too low. But then, they added a single variable, an external perturber, a hidden mass, something that wasn't supposed to be there according to our standard models. And when they added it, the simulations suddenly clicked. The cluster appeared. The objects fell inward. The timing matched the observations. The researcher, quietly and with visible reluctance, reportedly told a close circle of colleagues, "I don't know what it is. I can't tell you its mass or its orbit, but something is out there. The data is insisting on it." Clinging is it? What could perturb the Oort Cloud on a scale large enough to be noticeable over just a few years of human observation? A rogue planet, cast out from its own star system and now drifting through the interstellar night. A dark matter substructure, a phantom of the cosmic web. Something even stranger, something that doesn't interact with light at all, only with gravity. And if it exists, why does it remain hidden? Why have our surveys, our painstaking scans of the sky, failed to find it? Because if there is one thing that scientists, with their devotion to empiricism and observation, truly despise, it is the concept of invisible forces. Invisible forces feel like magic, and science is not supposed to need magic. Science is supposed to explain things through observable, testable phenomena. But right now, we don't have a clean explanation. We have a cluster, a pattern, and a growing, gnawing suspicion that the outer solar system is hiding something big. And speaking of hidden things, there is one particular candidate, one ghost that has haunted astronomy for nearly a decade. One hypothesis that explains so much, yet remains frustratingly, provocatively elusive. It is called Planet 9, and it might just be the key to understanding everything. Ghost stories are compelling because they are falsifiable. You cannot prove a ghost does not exist. You can only fail to find one, and that failure can always be explained away. It was the wrong night, the wrong house, the wrong medium. Planet 9 is the ultimate ghost story of modern astronomy. A massive planet, perhaps 5 to 10 times the mass of Earth, lurking in the outer solar system, far beyond Neptune. It would be too faint, too distant, too slow-moving to have been easily detected by previous surveys, a phantom presence whose existence is inferred only through the subtle, gravitational tugs it exerts on other, smaller objects. It is a theory that is both elegant and maddening. The hypothesis emerged in 2016 from the minds of Konstantin Batygin and Mike Brown at Caltech. They noticed something peculiar: a cluster of distant trans-Neptunian objects, TNOs, icy bodies like Sedna that orbit far beyond Neptune, had orbits that were strangely aligned. Their perihelia, the points where they come closest to the Sun, were all grouped together in the same region of space. Furthermore, their orbital planes were tilted in a similar way. This is profoundly weird. In a randomly distributed, gravity-dominated system, these orbits should be scattered, their orientations random. The odds of this alignment happening by chance are astronomically low. Unless, Batygin and Brown argued, something is shepherding them. Something massive, with enough gravitational influence over millions of years to corral these distant objects into similar orbital paths. They proposed Planet 9, a super-Earth, likely ejected from the inner solar system during the early chaotic period of planetary migration. It was kicked outward by a gravitational slingshot from Jupiter or Saturn, settled into a distant, eccentric and inclined orbit, and it has been out there ever since, invisible and silent, but gravitationally active, slowly sculpting the architecture of the outer solar system. Hypothesis is powerful and elegant. It explains the orbital clustering of the TNOs. It explains some of the peculiar inclinations of other objects. It even makes predictions about where else we should find similarly shepherded objects. There is just one rather significant problem: nobody can find it. Dedicated surveys have scanned the swathes of sky where it is predicted to be. Deep imaging campaigns have turned up nothing. Infrared searches, which might detect the faint heat signature of a large, cold planet, have found no trace. If Planet 9 exists, it is either fainter than expected, in a different location than predicted, or both. And that is where the waters get murky. Blindness. In recent years, new papers have further complicated the picture. Some have provided additional, indirect evidence supporting the Planet 9 hypothesis, pointing to new populations of TNOs with strange orbits that seem to require a massive perturber. Others have proposed alternatives. One compelling alternative is the self-gravitating disk model. Instead of a single massive planet, imagine that the outer solar system contains a disk of thousands of smaller bodies, with a combined mass significant enough for their collective gravity to interact. Clumps could form within this disk, and these clumps could perturb the orbits of the TNOs, creating the observed clustering without the need for a single large shepherd. It is a system of collective gravity, an emergent structure. No Planet 9 required. Is the phantom perturber. This is the idea that the gravitational signature we are seeing is not from a physical object at all. Perhaps it is the lingering gravitational wake of a transient structure that passed through the outer solar system millions of years ago, a dense cloud of dark matter, for instance, and is now gone. Or perhaps it is an artifact of how we model gravity itself at these extreme distances. The math might work, the observations might fit, but there might be nothing actually there. Here is why this all matters profoundly for Bernardinelli-Bernstein. If Planet 9, or some other massive perturber, does exist, it could have been the very object that nudged BB inward. It could have destabilized BB's orbit millions of years ago, setting it on its long, slow collision course with the inner solar system. In this scenario, BB is not a random comet. It is a victim, an object pushed by an unseen force, a piece of evidence in a larger gravitational mystery. And those same forces could be pushing others right now. But what if Planet 9 doesn't exist? What if the orbital clustering is just statistical noise, a fluke of small number statistics? What if we are, as humans are wont to do, seeing patterns in the random scatter? Then BB's journey is random. It is chance. It is cosmic roulette. And that is, in a way, almost scarier. Because randomness means fundamental unpredictability. It means we cannot forecast what is coming next. We cannot prepare. We can only watch, react, and hope that the next giant to fall inward is on a benign path. Some researchers are now arguing that the Planet 9 signal itself might be a statistical mirage. Our surveys are biased. They focus on certain regions of the sky where it is easier to find objects. Bright objects get noticed. Faint ones are missed. When you correct for these complex observational biases, the argument goes, the orbital clustering might simply disappear. The entire elegant hypothesis could collapse, and Planet 9 would become a mathematical ghost, a convenient placeholder for our ignorance. But then there are the true believers. The astronomers who have spent years refining the models, who have mapped every possible hiding spot, who have run ever more sophisticated simulations. They are not giving up. Because even if Planet 9 is not exactly where they first thought, even if it is fainter or smaller or on a slightly different orbit, the gravitational effects on the outer solar system feel too real to dismiss. Something, they insist, has to be out there. And then there is the truly speculative fringe, the ideas that make mainstream astronomers shift uncomfortably. What if Planet 9 isn't a planet at all? What if it is a primordial black hole? A tiny, city-sized black hole formed in the first fraction of a second after the Big Bang, with a mass equivalent to 5 Earths. It would have the perfect gravitational signature. It would explain why we cannot see it. It emits no light, only a faint whisper of Hawking radiation. And it would be one of the most bizarre objects in the entire solar system. Or maybe it is a dense knot of dark matter. We know dark matter clumps on the scale of galaxies, but could it form smaller planetary mass concentrations? Could there be a ball of pure dark matter, invisible to every instrument we possess, orbiting our Sun? Some physicists say it is possible. Others say the physics forbids it. Nobody knows for sure. Shall we hear a story about an astronomer who once joked, "If I find Planet 9, I'll name it after my dog." But then he added more soberly, "I might never find it. The outer solar system is vast, really, truly vast. Searching for a faint object in that much space is like searching for a single specific needle in a haystack the size of a continent. You could search for a lifetime and miss it by a few degrees, or it could be right there, hiding in the glare of a bright star, and you'd never know." But here is the existential question that lies beneath all the speculation. Does it matter? Does it matter if Planet 9 is a planet, a black hole, a dark matter clump, or nothing at all? Because regardless of the what, the effects appear to be real. Objects are being perturbed. Bernardinelli-Bernstein is falling inward. The clustering of unusual objects is a fact we have observed. Something, somewhere, is pulling gravitational strings in the outer darkness. And that something, whatever its nature, could tell us profound things about how planetary systems form and evolve, about the population of unseen objects in our galactic backyard, about what is possible in our universe. And maybe, just maybe, this line of questioning forces us to reconsider Bernardinelli-Bernstein itself. Maybe BB isn't even a comet in the traditional sense. Maybe it is something else entirely, something that challenges our very definitions, something that sits on the blurred boundary between comet and planet, between natural and unnatural, between the expected and the impossible. Because the more we learn about BB, the more it feels fundamentally wrong, not just unusual, but wrong, as if it doesn't quite belong in the neat categories we have built for the solar system. And that raises the most uncomfortable question of all. What, in the name of science, is Bernardinelli-Bernstein? In the world of astronomy, definitions are not merely semantic exercises. They are the foundational pillars upon which we build our understanding. They dictate how we think about objects, how we prioritize their study, how we allocate precious resources, and how we classify them in the grand family tree of the cosmos. And right now, Bernardinelli-Bernstein is a bull in the china shop of astronomical classification. By every traditional surface-level measure, BB is a comet. It displays a coma. It has active, gas-spewing jets. It is venting volatile materials as it approaches the Sun. These are the textbook definitions of cometary activity. But by its size, its internal structure, and its likely composition, it is something else entirely. It might be a dwarf planet. And if that is true, then everything we thought we knew about comets and about the contents of the Oort Cloud must be rewritten. Let's start with the most obvious piece of evidence: size. BB's nucleus is approximately 85 miles, 137 kilometers in diameter. This number is so far outside the norm for comets that it exists in a different realm altogether. Typical short-period comets are a few kilometers across. The absolute largest comets we knew of before BB, like Hale-Bopp, were perhaps 40 to 60 kilometers in diameter. BB is more than twice that size. It exists in the size range of dwarf planets. Pluto's moon, Charon, is about 1,212 kilometers across. Ceres, the largest object in the asteroid belt, is about 940 kilometers. While BB is smaller than these, it is in the same league. It is not a dirty snowball, it is a world. Then, there is the shape. The Hubble images that revealed BB's near sphericity are a game changer. This is a critical detail. Small objects, held together by nothing more than their own weak chemical bonds, are irregular. They are lumpy, potato-shaped, their forms dictated by chance accretion and collisions. But when an object becomes large enough, its own self-gravity becomes the dominant force. It pulls itself inward, overcoming the material strength of the rock and ice, and molds itself into the shape of lowest potential energy, a sphere. This state is known as hydrostatic equilibrium, and it is one of the three formal criteria the International Astronomical Union uses to define a planet or a dwarf planet. BB appears to satisfy this condition. This suggests significant internal pressure and self-gravity. It suggests that BB is not a fragile rubble pile, but a consolidated, structured body with geological integrity. Now, consider the composition as revealed by ALMA. The powerful, persistent jets of carbon monoxide are not just evidence of volatility, they are evidence of a specific internal architecture. To have massive, preserved reservoirs of hypervolatile CO after 4.5 billion years requires a differentiated structure. It requires layers. On a simple, homogeneous comet, CO near the surface would have sublimated away eons ago. But if BB is differentiated, if it has a layered interior with heavier materials like rock and metal having sunk to the core, and lighter ices forming a mantle and crust, then the CO could be trapped deep within, insulated by overlying layers of less volatile water ice and a refractory crust. This is not cometary behavior, this is planetary behavior. It is the same kind of differentiation that gave Earth its iron core and silicate mantle, that gave Pluto its possible subsurface ocean and nitrogen glaciers. Some scientists are now taking this a step further, proposing a cryovolcanic preconditioning model. The idea is that BB, over its billions of years in the Oort Cloud, experienced a low level of internal heating, not from the sun, but from within. Radioactive isotopes like aluminium-26, potassium-40, and uranium, which were abundant in the early solar system, would have been incorporated into its structure as it formed. As these elements decay, they release heat. In a small body, this heat quickly escapes into space. But in a large object like BB, the heat can be trapped, building up slowly over millennia. This internal warmth could have been enough to soften the deep ices, create liquid pockets, fracture the crust from within, and build up pressure. Imagine it like this. BB formed as a protoplanet, a building block for a larger world. But it was ejected before it could finish growing, kicked out to the Oort Cloud where it froze solid. But inside, the slow fire of radioactivity never went out. It has been simmering for eons, slowly preconditioning the interior. And now, as BB moves inward and solar heating adds to this internal warmth, the pressure is finally being released. The jets we see are not just simple sublimation, they are cryovolcanic eruptions, miniature volcanoes of frozen gas, driven by a combination of external heat and internal pressure. If this is true, if BB is a proto-dwarf planet with a warm, active interior, then studying it becomes incalculably valuable. We have studied comets, we have studied dwarf planets from a distance, but we have never studied a transitional object, something that is actively waking up, transitioning from a dormant, frozen world to an active, outgassing cryovolcanic body. It is a snapshot of a process we have never witnessed. What would this look like near perihelion? The spectacle would be unlike any comet passage in human history. We would not see a gentle, glowing haze. We could witness violent cryovolcanic eruptions, massive, sustained jets of gas and dust, perhaps launching material into a temporary, tenuous atmosphere. The surface could fracture before our eyes, with new vents opening and old ones collapsing. Chunks of the crust could break away, revealing the gleaming, pristine ice beneath. It would be a geological event on a planetary scale, and we would have a front row seat from a safe distance of nearly 11 AU. But here is the problem this creates. If BB is more planet-like than comet-like, then missions to study it become exponentially more important, and simultaneously, exponentially more difficult. Dwarf planets are complex geological worlds. To understand them, you cannot just fly past. You need to orbit, to map, to land, to probe. You need to understand their internal structure, their geology, their active processes. With our current technology, sending a mission to orbit an object 11 AU away on a highly inclined orbit is a pipe dream. It is nearly impossible. Not everyone accepts the dwarf planet hypothesis. Critics, applying Occam's razor, point out that BB's activity, while extreme, still consistent with normal comet behaviour, just scaled up. A bigger object has more volatile ices. Bigger reservoirs produce bigger jets. Nothing exotic like internal heat or cryovolcanism is strictly necessary. The simplest explanation is that it is just a very, very large comet. There is, however, a compelling middle ground, the hybrid object concept. Perhaps BB is a transitional form, not fully a comet, not fully a dwarf planet, but something in between, an evolutionary missing link. It could be a snapshot of how small icy worlds grow and change, how they differentiate, and how they eventually either become dormant or are destroyed. Studying BB could tell us how Pluto formed, how Eris formed, how all the dwarf planets in the Kuiper Belt and beyond came to be. There is a story of a planetary scientist who, after reviewing the latest Hubble and ALMA data, remarked to a colleague, "If this thing is a dwarf planet, then we just discovered a missing link in the family tree of the solar system, and we didn't even know we were looking for it." That is the beautiful, frustrating essence of astronomy. Sometimes the most profound discoveries are the ones you never set out to make, the objects that simply don't fit, forcing you to redraw the entire map. So, what is BB? Comet? Dwarf planet? Hybrid? The classification matters intensely. It determines the direction of study, the allocation of funding, the design of missions, and it fundamentally alters how we think about the population of the outer solar system. If BB is unique, it is a fascinating curiosity. But if BB represents a class of objects, if there are hundreds or thousands of similar proto-dwarf planets lurking in the Oort Cloud, then our understanding of the solar system's outer reaches is not just incomplete, it is fundamentally wrong. The outer solar system would be far more complex, far more active, and potentially far more dangerous than we ever imagined. And that line of thinking, that extrapolation from a single bizarre data point, brings us to the final, most speculative realm. The whispers. The quiet, private conversations where a handful of people, not many but some, are asking a bolder, more unsettling question. What if Bernardinelli-Bernstein isn't natural at all? Conspiracy theories, and the broader category of unconventional hypotheses, are born in the gaps. They flourish in the spaces where data is sparse, where explanations feel weak or unsatisfying, and where the human mind's powerful pattern recognition engine is left to run without sufficient fuel. And right now, Bernardinelli-Bernstein has gaps, significant ones. Its behaviour is anomalous in multiple intersecting ways. Its brightness is unusually stable for a comet. Its jets emerge from fixed, persistent locations. Its orbit is weirdly specific. And when the official mainstream explanations feel incomplete or are still being formulated, other people rush in to fill the void, sometimes with wild, unsubstantiated speculation, sometimes with uncomfortable questions that, while unlikely, force a valuable re-examination of assumptions, and sometimes, very rarely, with ideas that eventually turn out to be right. It is crucial to state this with absolute clarity. There is no evidence, zero, that Bernardinelli-Bernstein is anything other than a natural object. But there exists a whisper network, on internet forums, in niche blogs, in the comments sections of science news articles, of people pointing at these anomalies and asking, what if? So, let us address it. Not because it is likely, but because ignoring fringe theories does not make them disappear. It allows them to fester in the shadows, unchallenged by rational inquiry. Let us engage with the idea rationally, surgically, and see what, if anything, holds up to scrutiny. The first claim of the artificial hypothesis. BB's light curve is unusually stable. Most comets are erratic. As they rotate, they present different faces to the Sun, dark, inactive crust versus bright, active jets. This causes their brightness to fluctuate dramatically, sometimes by factors of 10 or more, over a single rotation. But BB's brightness changes are smooth, predictable, almost too regular. Proponents of the artificial theory argue that this suggests an underlying structural rigidity, like a manufactured object, not a loose, irregular rubble pile that would have a highly variable cross-section and albedo. If it is engineered, maybe that explains the stability. Non-existent from science is straightforward and compelling. Large objects rotate more slowly due to their greater moment of inertia. They also tend to be more spherical, which minimizes the change in cross-section as they rotate. BB is the largest comet we have ever seen by a huge margin. Its smooth, stable light curve is exactly what physics predicts for a large spherical body. No artificial structure is needed. It is simply behaving according to the scaling laws of nature. The second claim, the jets. ALMA's maps show the carbon monoxide jets emerging from specific, fixed regions on BB's surface, and these regions have remained active and persistent over years of observation. Some argue this feels designed, like the thrusters on a spacecraft, controlled, deliberate, and emanating from engineered ports. Plumbing the scientific counterpoint is, again, rooted in known geology. Comets, even small ones, often have active areas. These are specific regions where the surface is fractured or where the overlying refractory crust is thin, allowing subsurface ice to be exposed to sunlight. Once such a vent is established, it can remain active for the entire duration of a comet's passage through the inner solar system. The famous jets on Comet 67P Churyumov-Gerasimenko, studied by Rosetta, did exactly this. Persistent, localized venting is a natural product of cometary geology and insulation, not a sign of engineering. The third claim, the orbit. A 95.5-degree inclination, nearly perpendicular to the ecliptic. Some argue that this feels placed. Why would a natural object have such a specific, extreme trajectory? It feels like something that was deliberately inserted into this orbital plane. The counterpoint is dynamics. The Oort Cloud is a sphere, and objects within it can have any inclination. While highly inclined orbits are a minority, they are a predicted and natural outcome of the gravitational scattering that placed objects there billions of years ago. A perpendicular orbit is unusual, but not impossible. It points to a violent, dynamical history, not an intelligent designer. Scientifically, the artificial hypothesis collapses, but let us, for a moment, engage in the speculation. Let's play the game. If BB were artificial, what would that even mean? What could it be? Quietly is the probe. Perhaps BB is an alien spacecraft, a von Neumann probe sent by an advanced civilization to study our solar system. It is disguised as a comet to avoid detection, to appear natural and unthreatening. It moves slowly to gather data over millennia, a patient, long-term observatory. It is a romantic idea, but it raises more questions than it answers. Why disguise it so perfectly? Why not communicate? Why wait billions of years to activate? And how would any civilization build something 137 kilometers across? Psychologists are the storage facility. Maybe BB is a data vault, a cosmic library of Alexandria, built by a civilization that wanted to preserve its knowledge across deep time. They hollowed out a comet or built a structure and filled it with some form of ultra-durable data storage, crystalline matrices, atomic-scale engravings. They sent it drifting through the galaxy, a message in a bottle, waiting for another technological species to discover and decode it. A third idea is the seed ship. Perhaps BB is a terraforming vessel, a bioark filled with microorganisms, genetic material, or even nanotechnological assemblers sent to colonize new star systems. It drifts until it encounters a suitable star, then activates, releasing its payload to begin the slow process of transforming a dead world into a living one. Disregard ideas are fun. They are the stuff of grand science fiction, but they are not science. The reason is simple. Every one of these scenarios requires assumptions that are not supported by a single shred of data. BB's spectroscopy reveals only normal, cometary molecules: carbon monoxide, water, cyanogen, and simple organics. There are no exotic compounds, no artificial isotopic ratios, no laser emissions, no radio signals, no thermal signatures of internal power sources, nothing that screams engineered. Scientists who specialize in the search for extraterrestrial intelligence, SETI, test these hypotheses all the time. They model what an artificial object's light curve would look like, what its thermal emissions would be, how its rotation would behave. Every test when applied to BB comes back negative. BB behaves in every measurable way like a natural object. A weird one, yes. An unprecedented one, absolutely. But natural. Yet, the whispers persist, and there is a profound psychological reason for that. Humans are pattern-seeking creatures. We crave meaning. We desire agency. We are hardwired to see faces in the clouds and hear voices in the wind. We want to believe we are not alone in the immense, cold cosmos. And when we encounter something that truly does not fit our models, something as singular as Bernardinelli-Bernstein, a part of our psyche cannot help but wonder, could this be it? Could this be the sign we've been waiting for? The answer, based on all available evidence, is almost certainly no. But that almost is doing a tremendous amount of work in that sentence. It is the crack through which doubt and wonder seep. And here is the truly uncomfortable, philosophical truth that this line of questioning reveals. If an advanced civilization did want to send something through our solar system, disguising it as a comet would be a brilliant strategy. It would be the perfect camouflage. It would move slowly and naturally. It would be unthreatening. We would assume it was one of ours. We would study it with all our tools, perhaps even land on it. And by the time we realized what it truly was, it might be too late, or too far, or too strange for us to comprehend. That is the ultimate nightmare scenario for planetary defense and SETI, and it is almost certainly not happening with BB. But almost certainly is not definitely, and we will not know for sure until we get a closer look, until we send a probe, until we see its surface up close and confirm, definitively, that it is just a rock, just a piece of ice, just a magnificent natural relic from the early solar system. But sending a probe, that is the real problem. Because getting to Bernardinelli-Bernstein is a challenge so immense it borders on the impossible. Crimson missions are hard. This is a truth that cannot be overstated. Getting a spacecraft from the surface of Earth to another planet requires precision engineering, enormous amounts of energy, years of planning, and a healthy dose of luck. But a mission to Bernardinelli-Bernstein, that exists on another level of difficulty entirely. It is a challenge that makes a mission to Mars look like a weekend drive to the countryside. Because BB is not just distant, it is on a wildly different orbital plane, and it is moving through a region of space where the sun's light is feeble and communication is agonizingly slow. Flooring of the problem is delta V. This is the term rocket scientists use for the change in velocity required to accomplish a mission. More delta V means more propellant. More propellant means a heavier spacecraft. A heavier spacecraft requires a bigger, more expensive rocket. It is a vicious cycle of escalating mass and cost. For reference, a mission to Mars requires about 6 kilometers per second of delta V. A mission to Jupiter, about 9 kilometers per second. A mission to BB, with its extreme 95-degree orbital inclination, would require a staggering 15 to 20 kilometers per second or more. This places it in the realm of the most ambitious outer solar system missions ever conceived, like the Voyager probes or New Horizons, but with an added, back-breaking constraint, the plane change. Changing a spacecraft's orbital inclination is one of the most expensive maneuvers in all of orbital mechanics. To shift from the ecliptic plane, where all our rockets launch, to BB's near-perpendicular orbit requires a monumental amount of energy. There is really only one plausible, albeit still incredibly difficult, mission architecture: a Jupiter gravity assist. The idea would be to launch a spacecraft toward Jupiter. As the spacecraft flies past the giant planet, it would use Jupiter's immense gravity as a slingshot, not just to gain speed, but to bend its trajectory violently, cranking its orbital plane up by dozens of degrees, redirecting it into BB's path. After this dramatic maneuver, the spacecraft would then embark on a cruise of years, perhaps even decades, to finally intercept BB at a distant point in space. The launch window for such a mission would be incredibly tight, probably confined to a period between 2030 and 2034. After that, the orbital geometry of Jupiter and BB would become unfavourable, and we would have to wait decades for the next alignment. So, if we are going to do this, the decision needs to be made now. But even if we solve the trajectory problem, a host of other equally daunting challenges remain. First, power. At 11 AU from the Sun, where the rendezvous would likely occur, sunlight is only 1/121st as strong as it is at Earth. Solar panels are virtually useless. The spacecraft would need a nuclear power source, a radioisotope thermoelectric generator, RTG. But RTGs are incredibly expensive, politically sensitive due to their plutonium-238 fuel, and in very limited supply. NASA has a small stockpile, but they are allocated to flagship missions like the Mars Perseverance rover or the upcoming Dragonfly mission to Titan, not to a high-risk, speculative comet flyby. Deported. Communication. At 11 AU, the one-way light time is over an hour. A signal from the spacecraft would take over 60 minutes to reach Earth, and any command from Earth would take another 60 minutes to get back. This 2-hour round-trip delay makes real-time control impossible. The entire flyby sequence, the pointing of instruments, the course corrections, the data management, would have to be pre-programmed and executed with perfect autonomy. If something goes wrong in the final minutes of the approach, there is nothing mission control can do. They would be watching a drama that had already concluded an hour ago. Flooring. That NASA will be actively outgassing. This creates a coma, a cloud of gas and dust that scatters light and makes it incredibly difficult to see the solid nucleus clearly. A successful flyby mission needs to get within a few hundred kilometers to obtain high-resolution data. Navigating through the obscuring coma to achieve a precise flyby of a tiny, faint nucleus is a monumental challenge. A miss by even a small margin would result in billions of dollars being spent on a handful of fuzzy, long-distance images. Fourth, thermal control. The spacecraft would be operating in the deep cold of the outer solar system, where temperatures are hundreds of degrees below zero. It must be kept warm enough for its electronics to function, while also dealing with the heat its own systems generate. This thermal balancing act in the vacuum of space is a complex and mass-intensive engineering problem. Configured. When mission planners look at this constellation of challenges, the extreme delta V, the need for nuclear power, the light speed delays, the navigation hazards, and the thermal woes, most simply walk away. The risk is too high, the cost is too high, likely running into the many billions of dollars, and the scientific return, while fascinating, is often deemed insufficient to justify the investment when weighed against other priorities. You could fund 3 entire Mars rover missions for the price of 1 BB flyby, and Mars consistently delivers a high scientific return per dollar. But there is a small, dedicated group of mission designers and planetary scientists who refuse to give up. They have been quietly drafting concepts for a ghost mission. This would be a lightweight, minimalistic probe, carrying perhaps just a high-resolution camera and a compact spectrometer. It would be launched as a rideshare, piggybacking on another mission's rocket to reduce costs. It wouldn't orbit BB. It wouldn't land. It would be a simple, fast flyby, a cosmic drive-by shooting. It would scream past BB at several kilometers per second, snapping a few dozen high-resolution pictures and taking a few crucial spectral readings during the brief encounter, then spend the next year slowly transmitting the precious data back to Earth. This ghost mission has never been officially proposed. It lives in the realm of PowerPoint presentations and back-of-the-envelope calculations. But the idea is there, a testament to human curiosity. If a sudden influx of funding appeared, if political will miraculously aligned, it could, just barely, happen. There is also hope in future technology. Solar sails, which use the pressure of sunlight for propulsion, could eventually make high delta-V missions more feasible. Nuclear electric propulsion, which provides a gentle but continuous thrust for years, could also change the equation. But these technologies are not ready. They are not proven, not flight-tested. And by the time they are mature, Bernardinelli-Bernstein will be gone, receding into the outer darkness, its secrets intact for another 1,000,000 years. So, we are stuck. We have a unique, ancient, world-altering object approaching our neighbourhood. An object that could tell us how the solar system formed, how dwarf planets evolve, and what the Oort Cloud is truly made of. And we might never touch it. We might never study it up close. We will be forced to watch from a distance, to take our pictures and analyse our spectra from 1 billion miles away, and always wonder if we are missing the crucial piece of the puzzle, the one that can only be found by being there. Submerged emotional tension, this profound frustration, is real. Because science is not just about accumulating knowledge, it is about curiosity. It is about the primal urge to push boundaries, to reach out and touch the unknown. And when the universe dangles something so wondrous just out of reach, it hurts. It is a stark reminder of our limitations, of how small we are, and how trapped we can feel on this single pale blue dot. But here is the thing. Even if we cannot send a probe, we are not powerless. Earth-based telescopes are now incredibly powerful instruments. Hubble, ALMA, and the new James Webb Space Telescope are capable of feats that were unimaginable a generation ago. They can analyze the atmospheres of planets orbiting other stars. They can map the molecular clouds in distant galaxies. And they can study Bernardinelli-Bernstein. They can watch it evolve, track its jets, measure its composition, and piece together its story from right here at home. So maybe we don't need a mission. Maybe we already have the tools we need to understand this giant. Maybe the real breakthrough isn't about touching BB. It is about understanding it from here, using the incredible remote sensing power we have already built. Maybe that will be enough. Or maybe it won't. Maybe there is something on BB's surface, some mineralogy, some chemistry, some geological feature that we will never see from Earth. Some crucial, paradigm-shifting piece of the puzzle that requires a close-up look, a physical sample. And we will never know what it was, because we didn't go. Because we chose safe, predictable missions over a risky, ambitious leap into the unknown. And future generations of scientists will look back at this moment and wonder, with a sense of loss, why didn't they try? That is the weight of this moment. That is the responsibility. Bernardinelli-Bernstein is coming. Whether we study it up close or from afar, whether we fully understand it or not, its passage will irrevocably change how we think about the outer solar system, about comets, about what is possible out there in the dark. And the real question isn't whether we have the technology to get there. It is whether we, as a species, have the courage to try. Blackmail, for all its brilliant stars and dazzling galaxies, is mostly invisible. This is not a philosophical statement. It is a cold, hard fact of modern physics. Roughly 85% of all the matter in the cosmos is dark matter. We cannot see it. We cannot touch it. We cannot detect it directly, no matter how hard we try. We only know it exists because of its gravitational grip on the things we can see. Galaxies rotate too fast to be held together by their visible stars alone. Clusters of galaxies contain far more mass than the sum of their luminous parts. Something invisible, something that does not interact with light, is pulling the strings. We call this something dark matter. For decades, cosmologists have operated under a simplifying assumption that dark matter is smooth, that it forms a vast, diffuse, and relatively uniform halo around galaxies, a gentle gravitational fog that provides the scaffolding for the visible universe. But in 2025, that comforting assumption began to crack. New, high-precision gravitational lensing studies, combining data from the European Space Agency's Euclid Space Telescope with powerful ground-based surveys, revealed something unexpected. Dark matter is not smooth. It is granular. It is clumpy. It has a complex substructure that is far more pronounced than anyone had predicted. The lumps and filaments of dark matter appear to be smaller, denser, and more numerous than our best cosmological models allowed. To understand how this works, we need to understand gravitational lensing. It is a dramatic confirmation of Einstein's theory of general relativity. The idea is that a massive object, a galaxy, a cluster, warps the fabric of space-time around it. When light from a more distant background object travels through this warped space-time, its path is bent, like a car driving over a hill. The massive object acts as a lens, distorting and often magnifying the image of the background galaxy. By meticulously analysing these distortions, these cosmic funhouse mirrors, astronomers can map the distribution of the lensing mass. And since most of that mass is dark matter, they are, in effect, creating a map of the invisible. The 2025 breakthrough came from a team that applied sophisticated new statistical algorithms to these lensing maps, reconstructing the dark matter distribution in our local cosmic neighbourhood with a resolution that was previously unimaginable. Instead of a smooth, featureless halo, they saw intricate structure, filaments, nodes, and concentrations of dark matter that were far denser than expected, on scales of just a few light years. This was a shock to the system of cosmology. Now here is where this esoteric discovery collides with the story of Bernardinelli-Bernstein. The Oort Cloud, the home of BB, sits at the very edge of the Sun's gravitational domain, roughly 1 light-year out. It is immersed in the galaxy's dark matter halo. If dark matter clumps exist on the scale of light years, as the new data suggests, then these clumps could, from time to time, pass through or very near the Oort Cloud. And when they do, they exert gravity. It is an exceedingly weak force, yes, but gravity is cumulative, and it operates over astronomical timescales. Over millions of years, the weak, repetitive, gravitational tugs from passing dark matter clumps could perturb the orbits of Oort Cloud objects. Could these invisible, granular structures be the unseen forces nudging giants like BB inward? It is a wildly speculative idea, but it is not, in principle, impossible. Here is the problem. Dark matter, by its very definition, interacts only through gravity and possibly the weak nuclear force. It does not collide, it does not scatter light, it just pulls. And individual dark matter particles have minuscule mass. Even a clump of dark matter would have a relatively weak gravitational influence compared to, say, a passing star or a Jupiter-sized planet. So, could it really affect comet orbits in a meaningful way? The math is fiendishly complex. Some cosmologists run the calculations and say yes, it is possible. If the clumps are dense enough and pass close enough, their cumulative gravitational effects over billions of years could indeed perturb distant Oort Cloud objects, providing a slow, steady drizzle of inward-falling comets. Others are skeptical, arguing that the effects would be too small, too diffuse, lost in the much stronger noise of galactic tides and stellar flybys. Homelessness. There is a story, perhaps amplified in the telling, of a cosmologist who, after running new simulations incorporating these granular dark matter models, told their team something unsettling. If I'm right, I just handed Oort Cloud dynamicists a wild card. Because if dark matter can clump this densely, we need to rethink everything we know about outer solar system dynamics. Every perturbation calculation, every comet injection rate, everything. The implications are, indeed, enormous. If dark matter shapes comet orbits, then predicting future inbound objects becomes a nightmare. Because dark matter is invisible, we cannot track it. We cannot predict its movements. It is a random, unseen influence, like trying to predict the trajectory of a billiard ball on a table, where invisible hands are randomly tapping the surface. This ties back to BB in a profound way. BB's orbit, its timing, its unusual inclination, all of these anomalies might be influenced, however faintly, by the dark matter substructure of our galaxy. Maybe BB isn't responding to a hidden planet or a passing star. Maybe it is responding to the gravitational wake of a dark matter structure that passed through the Oort Cloud 10 million years ago, gave it a tiny push, and then moved on, leaving no trace except for the object itself, now on a new path. Future research will desperately try to test this, forging a new interdisciplinary link between cosmology and solar system dynamics. Scientists will build models that simulate how dark matter clumps evolve over time, where they go, and how often they interact with the Oort Cloud. It is ambitious, frontier science, and it has the potential to completely rewrite our understanding of how comets are sent toward the Sun. But this leads to an existential question. If dark matter, the largest scale structure in the universe, can shape the orbits of objects in our own backyard, what does that say about our place in the cosmos? It says we are more connected to the grand cosmic scheme than we ever imagined. It says that galaxy-scale structures have a direct, tangible influence on local events. That the Milky Way's dark matter halo is not just a passive backdrop, it is an active, dynamic participant, shaping our solar neighbourhood in ways we are only beginning to glimpse. And if that is true, then studying Bernardinelli-Bernstein is no longer just solar system science. It becomes a branch of cosmology. It becomes a unique, nearby laboratory for understanding how dark matter works, how it clumps, and how it interacts with the visible universe. That makes BB even more valuable, even more mysterious, and infinitely more important. Our solar system, for all its apparent order, is fundamentally crooked. The Sun, the anchor of our entire cosmic neighbourhood, spins on its axis. It has an equator, just like the Earth, and that equator is tilted. It is canted at an angle of about 6 degrees relative to the ecliptic plane, the flat disk in which all the planets orbit. 6 degrees may not sound like much, but in the context of celestial mechanics, it is bizarre. It is a glaring architectural flaw in an otherwise elegant design. The solar system formed from a collapsing, spinning cloud of gas and dust. That cloud flattened into a disk, and from that disk, the Sun and planets coalesced. Everything should have inherited that initial spin. The Sun's equator and the planetary orbits should be perfectly aligned. But they are not. This misalignment, known as the obliquity of the ecliptic, has puzzled astronomers for centuries. How did the Sun get tilted? Was it born this way? Or was it knocked askew by some ancient violent event? In 2025, new research, combining exquisite data from NASA's Juno mission to Jupiter with the European Space Agency's monumental Gaia star catalogue, forcefully reopened this ancient mystery. Juno spent years orbiting Jupiter, mapping its gravitational field with insane precision. Buried within that data are clues not just about Jupiter, but about the formation and early evolution of the entire solar system. Gaia, meanwhile, has provided a precise, three-dimensional map of the positions and motions of over 1 billion stars in our galaxy, allowing us to rewind the cosmic clock and see how our stellar neighborhood has changed over millions of years. When researchers combined these two monumental datasets, they were able to reconstruct the solar system's early dynamical history with a new level of accuracy. What they found was surprising. The Sun's tilt probably did not come from its formation. It was almost certainly imposed later by an external encounter. Something massive came close, a passing star, or perhaps a rogue planet, and its gravity exerted a torque on the young Sun, tilting its rotation axis relative to the steadfast plane of the planets. This matters for our story, because if such a dramatic encounter happened, if it was powerful enough to tilt the entire Sun, then it would have absolutely ravaged the infant Oort Cloud. It would have scattered objects, perturbed orbits, and created the population of high-inclination objects we see today. And maybe, just maybe, it was this specific cataclysmic event that set Bernardinelli-Bernstein on its current perpendicular path. Think about it. If a massive object passed through the outer solar system 4 billion years ago, it could have simultaneously done two things. Its gravitational torque tilted the young Sun by 6 degrees, and its gravitational scattering kicked a young protoplanet like BB into a wildly inclined orbit. Two profound effects, one single cause. And BB has been falling inward ever since, slowly, over billions of years, until its arrival in our era. Let's break down gravitational torque. When a massive object passes near a rotating body, it doesn't just pull on it uniformly. It pulls harder on the near side than the far side. This differential force creates a twist, a torque. If the torque is strong enough and lasts long enough, it can change the object's rotation axis. We see this all the time in the universe, moons becoming tidally locked to their planets, the spins of binary stars affecting one another. But applying this to the Sun is a staggering proposition. The Sun is monstrously massive. To change its spin axis requires an enormous force. So whatever passed by had to be huge, and it had to come uncomfortably close, probably within a few hundred astronomical units, a stone's throw in cosmic terms. Penetrated dado data is the key here. By measuring Jupiter's gravitational field in such detail, scientists can infer how the planet formed and migrated in the early solar system. This, in turn, tells us about the gravitational environment of the time. When this information is fused with Gaia's map of how nearby stars have moved, researchers can work backwards, identifying potential stellar suspects that might have been the culprit in this ancient crime. The leading candidate is a star from the Sun's birth cluster. When our Sun formed, it was not alone. It was one of hundreds, perhaps thousands of stars born from the same giant molecular cloud. In those cramped early days, stellar encounters were common. So, picture the scene. 4.5 billion years ago, a sibling star from the same nursery passes within a few hundred AU of our young solar system. Its gravity reaches in, tugs on the outer planets, and, most importantly, grips the Sun's outer layers. Over the course of an encounter lasting thousands of years, the Sun's rotation axis is slowly, inexorably, cranked over by 6 degrees. It's not enough to disrupt the planets, but it's enough to leave a permanent, telltale scar. There are alternative ideas, of course. Some suggest internal processes like magnetic braking. The Sun's magnetic field interacts with the solar wind, acting as a brake that slows its rotation over time. Perhaps this braking was asymmetrical, causing the tilt. The problem is, magnetic braking slows rotation. It doesn't typically tilt it. You'd need a severe asymmetry in the magnetic field or in the mass distribution of the young Sun, for which there is no evidence. Other theories propose asymmetries in the protoplanetary disk itself, with gas flowing in from one direction and creating a torque. But these explanations feel weak, requiring special, fine-tuned conditions. The passing encounter hypothesis is simpler, more robust, and explains multiple puzzles with one event. A planetary scientist reportedly ran thousands of Monte Carlo simulations, modelling different encounter scenarios. Only a narrow range of these encounters produced both the solar system's 6-degree tilt and the orbital distribution of Oort Cloud objects that includes BB's perpendicular orbit. This is not proof, but it is a compelling correlation. It hints at a profound truth. Our solar system did not evolve in isolation. It had visitors, it had close calls, and those violent interactions in its youth shaped everything we see today. The sun's tilt, the structure of the Oort Cloud, and the strange paths of comets like Bernardinelli-Bernstein. The simulations are a window into this violent past. You set up a young solar system, with planets still migrating, the Oort Cloud still forming. Then you introduce a passing star. Most of the time, it passes too far away and nothing happens. But occasionally, you get the perfect combination of mass, speed, and trajectory. And then, chaos. The sun tilts, the orbits of the outer planets shift, and the Oort Cloud is sent into a frenzy. Objects are scattered in all directions. Some are ejected into interstellar space. Others are thrown inward, onto long, looping, highly inclined orbits. Orbits just like BB's. Playoff. If one such encounter happened 4 billion years ago, could others have happened more recently? Some dynamicists think so. They propose that stellar encounters are not once-in-a-lifetime events, but rather a periodic drumbeat in the life of a star, happening roughly every 100 million years or so. Each close pass would send a new wave of comets inward, creating pulses of activity, clusters of unusual objects falling into the inner system. The evidence for this is controversial, buried in the statistics of comet arrival rates over millions of years. Some claim to see these pulses, others see only random noise. But if it's true, then Bernardinelli-Bernstein is not a solitary giant. It is part of a wave, and there are others already on their way, still too faint and distant for us to see. This is both thrilling and terrifying. It means the outer solar system is not a quiet backwater. It is a dynamic, active, and potentially dangerous frontier. But here is the truly unsettling part. If stellar encounters are the primary drivers of comet showers, then predicting future arrivals becomes nearly impossible. Stellar motions are chaotic. We cannot predict with any certainty when the next star will wander too close. It is a random, stochastic process. We can talk about statistical probabilities, one giant comet every million years, but we cannot say when the next one will come, or from where. We can only watch and wait, and hope our civilization is not in the way when the next giant falls. Understanding the solar system's tilt is more than an academic exercise. It is a fundamental question about our origins. It forces us to ask whether our system is typical or unusual, and the answer is, we still don't know. We need more data, more observations of other young star systems with the James Webb Space Telescope to see if tilted disks are common. The good news is that we are starting to get that data, and it shows that warped, asymmetric disks are not rare. Perhaps we are not special. Perhaps every planetary system is shaped by such violent beginnings. Or perhaps we got lucky. That ancient encounter might have cleared out dangerous debris, preventing a later catastrophic impact that could have sterilized Earth. Maybe we owe our existence to that cosmic near miss. The pieces of the puzzle are coming together. The Juno data, the Gaia catalogue, the simulations, the observations of other stars. All of it points toward a solar system whose history was shaped by external forces, by a chaos more profound than we once believed. And Bernardinelli-Bernstein is a living relic of that history, a survivor from an encounter that happened when the Earth was still molten, an object sent on a slow, billion-year journey inward, carrying with it the memory of an ancient violence. And now, finally, it is arriving. It is coming home. Or perhaps it is coming to tell us a story about where we came from, about how fragile our existence is, and about how the cosmos reaches out to shape everything, right down to the tilt of our own sun. When we zoom out, when we look at the universe on its very largest scales, it reveals a structure that is neither uniform nor random. It is a cosmic web. Vast, thread-like filaments of galaxies, millions of light-years long, intertwined and separated by even vaster voids, regions of space that are almost incomprehensibly empty. These are not small holes, they are bubbles of nothingness, some stretching for hundreds of millions of light years, containing only a handful of isolated galaxies, or, in some cases, nothing at all. And one of these voids is particularly strange. It is linked to a feature known as the CMB cold spot. This is not a story about our solar system, but about the universe itself, and how its largest structures might, in ways we are only beginning to imagine, be connected to the journey of a single comet. Polluted spot appears in the cosmic microwave background, CMB, the afterglow of the Big Bang. This is the oldest light in the universe, a snapshot of the cosmos, when it was just 380,000 years old, now cooled and stretched into the microwave part of the spectrum. The CMB is remarkably uniform, a thermal bath of radiation at 2.7 degrees above absolute zero. But it is not perfectly smooth. There are tiny fluctuations, variations of a few parts in 100,000, which are the seeds from which all the galaxies, stars, and planets eventually grew. And then there is the cold spot, a region in the constellation Eridanus that is significantly colder than the surrounding CMB. It is too large and too cold to be easily explained by the standard model of cosmology. Astronomers have been arguing about it for over 20 years. In 2025, a team reanalyzed the CMB data from the Planck satellite with new, more powerful statistical techniques and better noise filtering. What they found was unsettling. The cold spot was deeper, more extreme, and more statistically significant than previous analyses had suggested. It was a more profound anomaly than we had realized. Why does this matter for a story about a comet? Because the leading theory for the cold spot is that it is caused by a supervoid. The idea is that there is an enormous region of space, a void of truly epic proportions, between us and the CMB. When the CMB photons travel through this void, something strange happens due to the expansion of the universe, an effect called the integrated Sachs-Wolf effect. In simplified terms, the photons lose energy climbing out of the void's gravitational well, and because the universe is expanding, they don't get all that energy back. They end up slightly cooler, creating a cold spot in the CMB map. Greenville is the numbers. The supervoid needed to explain the cold spot using standard physics would have to be implausibly large and implausibly empty. It would push the boundaries of what we think is statistically possible in our universe. Not impossible, but highly, highly unlikely. This makes cosmologists nervous. It suggests that either we are incredibly unlucky to be looking at such a statistical fluke, or our understanding of physics on the largest scales is incomplete. Plunder this has led to more exotic explanations. Some cosmologists wonder if the cold spot is a window into something beyond our standard model. Perhaps it is evidence of a collision between our universe and another bubble universe in the multiverse. Such a cosmic collision could leave a scar, a specific pattern of cold and hot spots on the CMB. The math for this kind of bubble nucleation exists in some theories of eternal inflation, but it is highly speculative. Others propose that it reveals something about dark energy, that dark energy is not constant but varies from place to place, and that this supervoid is a region where dark energy behaves differently, accelerating the expansion more fiercely and creating the observed cold spot. Now let's take the speculative leap. A leap so vast it spans the entirety of the observable universe. If the cold spot is real, if it represents a genuine anomaly in the universe's large-scale structure, could its gravitational influence, however faint, affect local dynamics? Could it, in any conceivable way, be connected to the Oort Cloud and the journey of Bernardinelli-Bernstein? On the face of it, this sounds absurd. The cold spot is billions of light years away. BB is here, in our solar system. The connection seems preposterous. Crimson is infinite in range. It is weak at large distances, but it is cumulative. We already know that the gravitational pull of the entire Milky Way galaxy through galactic tides affects the Oort Cloud. So, what about the pull from larger structures? What about the gravitational influence of nearby galaxy clusters, of the great cosmic filaments, and of the vast supervoids? The calculations are brutal, dealing with forces so weak they are nearly negligible. Nearly. Some dynamicists have run simulations to see how external gravitational influences from the large-scale structure of the universe might affect Oort Cloud dynamics over billions of years. The answer is a tentative, fascinating maybe. The effects are tiny, but over the age of the solar system, these tiny effects could produce subtle changes in the orbital distribution of the most distant objects. If the cold spot is indeed a supervoid, and if that supervoid is relatively nearby in cosmic terms, its gravitational shadow, its lack of pulling power compared to the denser regions around it, could subtly influence the orbits of Oort Cloud objects. Not enough to send them falling inward on its own, but enough to provide a tiny nudge, a perturbation that makes them slightly more susceptible to other, stronger influences, like galactic tides or passing stars. And maybe, just maybe, Bernardinelli-Bernstein is one of those objects. Maybe its specific orbit was shaped, in an infinitesimally small part, by the gravitational landscape of the cosmos itself. Maybe the reason it is falling inward now is because billions of years ago, the universe's largest structures gave it a tiny, almost imperceptible push. A push that, when combined with all the other gravitational influences, eventually conspired to set it on its current trajectory. This is, let me be clear, wildly, extravagantly speculative. Most astronomers would dismiss it outright. The effects are too small, too diffuse. But a few are intrigued, because if it is even remotely possible, it forces a complete paradigm shift. It means we cannot model the Oort Cloud in isolation. We must see it as part of a connected cosmic system, influenced by everything from the planet next door to the void a billion light years away. A cosmologist, after reviewing the new cold spot data, reportedly joked with colleagues, "If the cold spot is a window, what's on the other side?" It was a joke, but it points to a real, profound question. If our universe is part of a multiverse, and the cold spot is where we touch another one, what are the consequences? The laws of physics could be different, constants could vary, and if energy or information can leak across that boundary, even for an instant in cosmic time, the effects, however faint, could propagate through the fabric of space-time. Subjected into the deepest realms of theoretical physics here, where science and philosophy blend. But this is the power of an anomaly like Bernardinelli-Bernstein. It forces us to ask the biggest questions. It connects the incredibly local to the unimaginably vast. Studying BB is not just about understanding a comet. It is a test case for how the universe works at every scale. From the quantum interactions in its ices to the gravitational pull of cosmic voids, everything is connected. BB is a messenger, and its message is that the cosmos is a single, incomprehensibly complex and deeply interconnected system. And we are only just beginning to learn how to listen. In the 21st century, the most powerful tool in an astrophysicist's arsenal is not a telescope, but a computer. We cannot rerun the formation of the solar system. We cannot experiment on galaxies. So we simulate. We build virtual universes inside silicon chips, encode the laws of physics, set the initial conditions, and let the code run, watching what emerges. But these simulations are brutally computationally expensive. To model the entire Oort Cloud, with its trillions of individual bodies tracking their gravitational interactions over billions of years, is a task that would take centuries on the world's fastest supercomputers. It is, for all practical purposes, impossible. Or it was. Enter artificial intelligence. In 2025, a research team unveiled a breakthrough, a neural network, a form of AI, trained on a hybrid dataset of cosmological simulations and real observational data. This AI could predict the formation of large-scale structure in the universe, the cosmic web of galaxies and voids, more accurately than the most sophisticated traditional simulations. And it could do it not just a little faster, but 1,000 times faster. This was not an incremental improvement, it was a revolution. Suddenly, simulations that were once pure fantasy became feasible. This AI doesn't work like a traditional computer program that solves equations step by step. It works by learning patterns. It is fed vast amounts of data, from previous simulations, from telescope observations, and it learns the underlying relationships, the hidden shortcuts, the emergent behaviors that human modelers might miss. It is pattern recognition on a cosmic scale, and it is incredibly, unsettlingly powerful. Researchers immediately began feeding it solar system data, the known orbits of planets, asteroids and comets, the positions of distant TNOs, and they asked it the ultimate question: where will the next Bernardinelli-Bernstein come from? The AI processed the request, its digital neurons firing through petabytes of information. After hours of computation, it spat out a prediction: a specific region of the Oort Cloud, a specific time frame, 20 to 30 years from now. The researchers were skeptical, as good scientists should be. They ran independent, traditional simulations to check. To their astonishment, the independent models supported the AI's prediction. The underlying orbital dynamics it had detected were real. But here is where it got uncomfortable. The AI also flagged secondary predictions, anomalies in the data, perturbations in the orbits of some distant objects that didn't seem to match any known gravitational influence from planets, tides, or passing stars. When the researchers pressed the AI, asking it to justify these anomalies, to explain the why, it couldn't. Its response was essentially, the pattern is there. It could identify the correlation, but it could not provide the causation. This is the double-edged sword of advanced AI. It might be seeing real effects that our current physics cannot explain, the gravitational signature of Planet 9, or a dark matter clump, or something else entirely. Or it might be hallucinating, finding spurious patterns in the noise, like seeing a face in the clouds. We won't know which is true until the future arrives, and we can check its predictions against reality. Plight. The potential, however, is staggering. Imagine combining the relentless all-sky gaze of telescopes like the Vera C. Rubin Observatory with the predictive power of this AI. We could forecast comet arrivals decades in advance. We could identify potentially hazardous objects long before they become an immediate threat. We could plan missions with a confidence we've never had before. Steinstein specifically, the AI is already being used to model its evolution. How will its jets change as it approaches perihelion? Will it fragment? The AI can run thousands of different scenarios in the time it takes a traditional computer to run one, testing the stratified chemistry model against the rubble pile model, the cryovolcanic hypothesis against simple sublimation. It is helping us converge on the truth faster than we ever thought possible. Poisoning raises a deep philosophical question for science. If an AI tells us something we don't understand, something that contradicts our cherished models, should we believe it? Should we trust the black box? Or must science demand a human understandable explanation for every prediction? There is a schism forming. Some scientists argue that human intuition is limited, evolved for life on the African savanna, not for grasping the dynamics of the Oort Cloud. We should trust the AI that can see patterns we are blind to. Others counter that science is about understanding, not just prediction. A model that predicts correctly but cannot explain why is alchemy, not physics. We need transparency. We need to be able to peer into the machine and comprehend its reasoning. For now, the AI is a tool, a supremely powerful one, that is already changing how we study the outer solar system. It is revealing that the Oort Cloud is far more dynamic and structured than we thought. It has detected potential waves of comet arrivals, pulses of activity that align with old, discarded theories of periodic comet showers driven by galactic tides. It is predicting asymmetries in the cloud itself, dense regions pointing toward constellations like Perseus. If these predictions are confirmed by observation, the AI will have rewritten our textbook maps of the solar system's boundary. Forging Bernardinelli-Bernstein is the perfect subject for this new partnership between human and machine intelligence. It is a problem of such complexity that it demands every tool we have. The AI sees the patterns in the noise. The human scientists ask why and design the experiments to find out. Together, they are unraveling the mystery. And what they are finding is that the universe is, as always, stranger, more complex, and more wonderfully mysterious than we dared imagine. Blackmail Hall of Physics departments, and in the digital corridors of preprint servers, a paper began to circulate in 2025. It was not published in a major journal, not at first. It spread through whispers, through email chains, through intense, late-night discussions. It proposed something so radical that most physicists dismissed it out of hand. But a few, a small and growing few, found its implications impossible to ignore. The paper suggested that our understanding of inertia, one of the most fundamental concepts in all of physics, might be wrong. Inertia is the resistance of any physical object. It is the oomph behind Newton's first law. An object at rest stays at rest. An object in motion stays in motion. It is woven into the very fabric of space-time in Einstein's general relativity. The paper proposed that this inertia is not a constant property of mass. It proposed that it might vary depending on the cosmic environment. Specifically, that in the deep dark of interstellar space, in the outer reaches of planetary systems where gravitational fields are weak and matter is sparse, inertia might be slightly different. Not dramatically, but measurably. Mass might resist acceleration a little more or a little less than our equations predict. The motivation for this heretical idea is a deep-seated frustration with dark matter. Dark matter works beautifully to explain the large-scale structure of the universe, but there are small, nagging anomalies at the edges of galaxies, slight discrepancies in the motions of some distant stars that dark matter models struggle with. What if, the paper's author argued, we are not missing a type of matter, but are instead misunderstanding a fundamental property of the matter we already have? What if Newton and Einstein's laws, while overwhelmingly successful, are still an approximation, and that in the extreme environments of the galactic fringe and the Oort Cloud, a deeper layer of physics begins to reveal itself? The criticism was swift and brutal. The math is elegant, one critic said, but where is the evidence? How do you test this? Another wrote in a review, "If you are right, you have just overturned 3 centuries of physics. Extraordinary claims require extraordinary evidence." The paper was rejected, resubmitted, and rejected again. But it found a small, dedicated audience. Physicists who had spent their careers wrestling with the shortcomings of the standard model of cosmology, who found the proliferation of dark matter and dark energy to be aesthetically unsatisfying. They didn't endorse the theory, but they were intrigued. They began running their own simulations, looking for any observational signature that could support or refute it. And this is where the story of Bernardinelli-Bernstein reaches its most profound and speculative peak. If variable inertia is real, then every single calculation we have ever done about the orbits of Oort Cloud objects is slightly, insidiously wrong. Not wrong enough to be obvious, but wrong enough to matter over the course of billions of years. Objects that have spent eons in the deep dark, where inertia is hypothetically different, would show the effects most clearly. Their orbits would deviate from Newtonian predictions in specific, subtle ways. Therefore, studying Bernardinelli-Bernstein's orbit with exquisite precision becomes a test, a way to check if the laws of physics as we know them hold true in the solar system's most remote frontier. If BB's path shows a deviation, a tiny anomaly that cannot be explained by any known gravitational influence, and if that anomaly matches the predictions of the variable inertia model, then this fringe idea suddenly gains a shred of credibility. It would not be proof, but it would be a data point. And if other long-period comets show similar deviations, the case would grow stronger. There is a story that the young physicist who wrote the paper received hate mail, being called a crank and a fraud. But they also received private messages of support from senior researchers who said, "Keep going. You might be wrong. You are probably wrong, but you might be right. And if you are right, everything changes." This is the nature of science at its cutting edge. It is uncomfortable. It is divisive. Most revolutionary ideas are in fact wrong, but some are not. Some are the first glimpse of a deeper truth, and we never know which is which until we test them, until we gather the data and let the universe itself be the judge. So, what is Bernardinelli-Bernstein? It is a comet. It is a dwarf planet. It is a time capsule. It is a gravitational puppet. It is a test of cosmic physics. It is all these things and more. It is a reminder that our knowledge is provisional, that our models are maps, not the territory, and that the universe is always ready to surprise us. BB is heading toward the sun, slowly, majestically, inevitably. It carries mysteries, frozen in ice for 4 billion years. And we are watching. With all the tools of our modern science, telescopes, radio arrays, supercomputers and AI, hoping to understand it before it swings past perihelion and retreats back into the darkness for another million-year journey. But here is the final, humbling truth. Even if we unlock all of BB's secrets, there will be others. More giants are lurking in the Oort Cloud. More anomalies are drifting in the dark. The cosmic drumbeat continues. Bernardinelli-Bernstein is not the end of a story. It is the beginning. It is the herald that has awakened us to the fact that the outer solar system is not the quiet, static place we once thought. It is a dynamic, chaotic, and wondrous frontier, and we have only just begun to explore it. This giant comet is a messenger, and its message is simple, terrifying, and exhilarating. We are not alone in our own solar system. We share it with giants, and they are stirring.